Oh, it's like, oh my goodness.
I was using some of that modern texting lingo that all the kids are using these days.
Are you kids talking? That's a sad part of senior year.
That is so true. Myself, I just cried.
All right. So we have talked about the idea that for z equals f of xy equals a constant. So when we say f of xy equals a constant, we get level curves. Similarly, for f of xyz, f of xyz equals a constant, we get level surfaces. So every constant we set this f of xyz equal to, we get a different surface. So we could imagine that surface being a level surface of a four-dimensional solid. But we get a surface. If we set f of xyz equal to a constant, we get a surface.
Wait, what?
So if we had, for example, x squared plus y squared plus z squared equals 4. That's a sphere.
Three-dimensional surface?
Yes.
Am I the only person that heard four-dimensional surface?
Oh, well, we can think of that three-dimensional, it's a level surface of a four-dimensional solid.
What is a four-dimensional solid?
A solid in 4 dimensions.
Something that when you slice it, you can
Right, when you slice it, you get a surface, a three-dimensional surface. Just like when you slice a three-dimensional solid, you get a two-dimensional curve.
How do you visualize a
No, I just debated it. I think it's
Haven't I told that joke before?
Like, that's a no problem on a quiz.
Haven't I told you that joke before about the engineer that couldn't see how to visualize higher dimensional surfaces, and the mathematician says, well, just let the dimension equal n and let n go to 4. Yeah.
How do you know since we've never encountered
All right. So for today, we're going to let r of t be a position vector. Being a position vector, this is a position vector of a curve on the surface f of xyz equals a constant. So I'm going to say r of t, I'm going to write it in terms of its components, x of t I hat plus y of t j hat plus z of t k hat. Well, since x, y, and z are on this surface, we can write that f of x of t, y of t, z of t equals a constant. Since this curve is on the surface, that's going to be true. And then we can use a chain rule to find the derivative of f with respect to t. So if we use a chain rule, that's going to be the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt plus the partial of f with respect to z times dz dt. And that's going to equal, the derivative of a constant is 0. Well, what is this quantity? df dx times dx dt, df dy times dy dt, df dz times dz dt. So we have this partial of f with respect to x, this x component times this x component, this y component times this y component, this z component times this z component. It's a dot product, right? Because del f is df dx, df dy, df dz, the vector. And what is this dx dt, dy dt, dz dt? R prime, right? Isn't that R prime? R prime is the vector dx dt, dy dt, oops, that's a straight d, that's a y, dz dt. So what we have here is that del f dot R prime equals 0. What does that tell us? They are orthogonal. And R prime, what do we know about R prime in terms of the curve R? Isn't it tangent to R? R prime is tangent to R. So R prime is tangent to R. So that means R is on the surface of the R is on this surface. So R prime is tangent to the surface. F of x, y, z to the surface f of x, y, z equals a constant. Well, that means that del f is orthogonal to the surface because R is an arbitrary position vector on an arbitrary surface. So del f is going to be orthogonal to any tangent vector at that point because R prime is arbitrary. So del f is orthogonal or normal to the surface. So it's going to be normal to f of x, y, z equals a constant. So if we have a surface, f of x, y, z equals a constant, del f is going to give us a normal vector to that surface.
So does this work for two-dimensionals? Would del f be normal to...
So we said last time del f is normal to the level curves.
Okay.
So for a surface, f of x, y, z equals a constant. So a level curve is f of x, y equals a constant. So del f is normal to the level curve. Here we have f of x, y, z is a constant. So del f is normal to the surface. So what we've just done is did a nice little proof of what we're going to write as, this is a theorem in our book. So I'm just going to write it out just in general. So del f is normal to a surface, f of x, y, z equals a constant at any point on the surface. So I'm going to write del f as a normal vector. So we're going to say if f of x, y, z, we need our function to be differentiable. So it needs to be a nice function. At a particular point, at p0 is x0, y0, z0. And we want del f at that point not to be 0. Because we know if del f is 0, then it's orthogonal to any vector there. Then we have these things. One, del f at that point so that's going to be a normal vector to f equals a constant at that particular point. I'll just say at p0. And this also means that del f at p0 is orthogonal to every tangent vector to f at p0. So if we think of a bunch of tangent vectors, put a bunch of tangent vectors together, then we get a plane. So we're going to use del f as the normal vector to what we're going to call the tangent plane. So the plane normal to del f at p0 is the tangent plane. To the surface at p0. So just like for curves, we talked about the tangent line. For surfaces, we can talk about the tangent plane. And the tangent plane will be able to get some information about the surface from the behavior of the tangent plane. And then we can also say the line through p0 in the direction of del f is the normal line. To the surface. So the normal line would be the line that goes in the direction straight up, essentially. The tangent plane would be the plane that is level. If you took the surface and turned it into a two-dimensional, you turned it into a flat surface, at that point the tangent plane would be what would represent the surface there. All right, we good? Let's draw a picture. So what we have here is a nice surface. Blanket, maybe, yeah, piece of toast, something like that. And here is our curve on the surface. And I'm going to say that is r of t on the surface. So at a particular point, from r prime, we get our tangent vector. So there is r prime of t. And I forgot to say the surface is f of x, y, z equals a constant. And then del F, I'll draw that in green, would be, whoops, green. There would be del F. And I'm going to say at P0, and we'll say this point is P0. And that's going to be orthogonal to R prime. And if we have plane, tangent plane at that point, del F would be the normal vector to the tangent plane. All right, and we can write, using this, our normal vector to the surface is n is going to be the vector, I'm going to write it in this notation, f sub x, f sub y, f sub z, so just del f. So that's our normal vector. If z equals f of x, y, so we have z equals x squared plus y squared, for example, then we can write f of x, y, z is f of x, y minus z, and that equals 0. So that's our, this will be our f of x, y, z equals a constant if we have our surface written as z equals f of x, y. And our normal vector to that surface is going to be df dx. I'll write f sub x again. F sub x, f sub y, -1. Partial of z with respect to negative z with respect to z is -1. And these will be our normal vectors, the normal vectors we can use to write the equation of the tangent plane. Because we'll know the point, we'll know P0. We have a point on the plane, we have our normal vector, and we can write our equation. So the components of the normal vector give us our direction numbers for our tangent plane. They also give us the direction numbers for our normal line. So this use of the gradient as a normal vector is, in chapter 15, is going to be the most important use of the gradient. The gradient is a normal vector to a surface. F of x, y, z is a constant. So our tangent plane at P0 is then f sub x, x minus x0, plus f sub y, y minus y0, plus f sub z times z minus z0 equals 0. Our standard equation of our plane. So that's how we're going to write the equation of our tangent plane. If z equals f of x, y, then we're going to use this as our normal vector. We're going to say f of x, y minus z equals 0 is our three variable surface equals a constant. Our equation is f sub x, x minus x0, plus f sub y, y minus y0, minus z minus z0 equals 0. And we can also use that these vectors. Those would be our vector in the direction of the normal line. And we can use those vectors then to write the equation of the norm, the parametric equations or the symmetric equations of the normal line. All right. Questions about tangent plane? Okay, let's look at some level surfaces. And then we will do a couple problems that have to do with tangent planes, and then we'll talk about one other piece of information that we can get from our tangent plane. This is one of the examples coming up is my it's close to my favorite example in this next section of chapter 13. All right, we want to describe the level surface. First one, f of x, y, z equals 3x minus 5y plus 3z minus 15. Describe the level surface, f of x, y, z equals 0. So we're looking at the surface 3x minus 5y plus 3z minus 15 equals 0. What is that thing? If we set that equal to 0, then 3x minus 5y plus 3z equals 15. That's a point.
Yeah.
And if we wanted to plot the plane, we set 2 coordinates equal to 0, plot a point on the x-axis, the y-axis, and z-axis, and we get a little triangle in the first octant, where it cuts through the first octant. F of x, y, z equals x squared plus y squared plus z squared minus 25. That's going to be a sphere, right? We get x squared plus y squared plus z squared equals 25. So that's a sphere. The third one, how about f of x, y, z is 4x squared plus 9y squared minus 4z squared, and that's our function. So we're saying that 4x squared minus 9y squared plus 9y squared minus 4z squared equals 0. So 4x squared plus 9y squared equals 4z squared. That's a cone. And it's going to be elliptical. So if we look at in the xz plane, 4x squared equals 4z squared. So x equals z. You get lines that are the size. Same thing here. Get lines the size, and here we get parallel to the z-axis. We get ellipses. So we get the straight sides, but they're connected with ellipses. Thank you. So elliptical cone. Number 4. F of x, y, z equals 16x squared minus 9y squared plus 144z. So we're saying 16 x squared minus 9y squared plus 144z.
Oh, it's a saddle.
Saddle hyperbolic parabola. Because this is going to give us hyperbolas. These are going to give us parabolas. So hyperbolic paraboloid, saddle shape, a Pringles.
If I coded a saddle on a test, would that be okay?
Yes.
So saddles like always follow that same thing. You have a
Mhm.
positive square and a negative square and a single.
Yeah, yeah.
Yeah.
Yep.
Yeah.
Mm-hmm. Yep, positive, negative. And then the sides of the saddles, like where your legs would go in the saddle, those are the hyperbolas. You know, you're putting your legs into hyperbolas when you sit in the saddle.
No, they're not really hyperbolas in a real saddle.
Oh.
That's because it's hard to make saddles in a perfect shape. So if they were perfectly shaped, they would be hyperbolas.
But they would be perfectly shaped for a horse.
Well, that's because horses aren't perfectly shaped. If horses were perfectly shaped, they'd be spherical, right?
No fault.
Can you imagine that? Spherical horse in a vacuum.
Spherical horse in a vacuum, right? With a hyperbolic paraboloid saddle. That's like a mathematician's dream. All right. So for this one, I don't want to go through the procedure. I just want us to see what this question is really asking us. What if we have a surface x squared plus y squared plus z squared equals 11, and we want a unit normal vector at 3, 1, 1. So what is this question asking us to do? Del f at 3, 1, 1, and then normalize it. So really what you're doing is normalizing the normal vector, right? You want a normal vector.
Is there the possibility that you could normalize something and if it's bigger?
Yeah? Yeah, if the magnitude was less than 1 and you normalized it, then the magnitude would be equal to 1. Yeah.
Why is it called normalized?
Because one is normal.
Wow, we filled in. It seems like it would be intellectual.
All right. Let's say f of xy is y over x. And we want to find the equation of the tangent plane and symmetric equations of the normal line at 5, 13, negative 12. All right, so what's going to be our first step here? We want to find del f, but we need f of x, y, z equals a constant. So what are we going to do with this? We're going to subtract z. So we're going to say f of x, y, z is y over x minus z, and that equals 0. That's going to be our f of x, y, z equals a constant. Because f of x, y, z f of x, y we can think of as z. So del f is going to give us our normal vector. We need to normalize that. So I've capitalized it because this f is different than that f.
Oh.
It's not the same f, different function. Del f gives us our normal vector. So del f is partial of this with respect to x minus y over x squared. I hat partial of this with respect to y 1 over x j hat, and then we get a minus k hat. Oh, I picked the wrong, these numbers from a different example. I want ones that work out a little nicer. Let's see. Where do I want it? 1, 2, 2. The other ones work out better in the different example. All right. So del f at 1, 2, 2 is going to be negative 2, comma 1, comma negative 1 when we plug those in. So those are our direction numbers for our, we don't need to normalize, we don't need a unit vector to write the equation of our plane. So our tangent plane, this is a point on the surface. That's going to be a point on the plane. So we're going to have negative 2x minus 1 plus 1 times y minus 2 minus z minus 2 equals 0. That would be the equation of our tangent. Do you remember how to write symmetric equations of a line?
Yeah. No.
Symmetric equations of our line.
Don't lie, Connor. Dylan.
We do x minus x0, x minus 1 over the direction number equals y minus y0 over the direction number equals z minus z0 over the direction number. If we wanted parametric equations of our line, it would be x equals, do you remember? Negative 2t plus 1. Yeah. All right, questions there? All right, this next one is one of my favorite examples here.
Another favorite example.
Second favorite example. The heat-seeking particle is definitely the first, but I like these kinds of problems. Let's say we have x squared plus y squared equals z. What is this?
Saddle.
No.
Paraboloid. That's a paraboloid. And z equals 4 minus y. We want, write symmetric equations of the tangent line to the curve of intersection. At 2, negative 1, 5. So what is this? What is this surface? A plane. In 3 dimensions, that would be a plane.
2D line, Dylan. Nice job, Connor.
Well, what are we going to do here? So
I'm the only one saying anything.
So we could try to set these two equal to each other and then parameterize that curve. That could be challenging. Okay, that's a good first step. So we have two surfaces. The gradient, if we have f of x, y, z equals a constant, del f is going to give us normal vectors to those two surfaces. So we have, here's a curve of intersection, for example. And we have, at this particular point, we have, I'm going to say del f1 and we have, I don't know, it doesn't have to look like it's, so that's del f2. I want to make it look like it's nothing special there. Del f2. So there's our curve, there's that point, there are the normal vectors at that point. What's going to give us a vector in the direction, or in the tangent to that curve of intersection? The cross product. We cross these two. That's going to be orthogonal to both of those. These are orthogonal to each surface. So the vector that's orthogonal to those two is going to be tangent to both surfaces at that point. So it's going to be tangent to the curve of intersection. So del f1 cross del f2 will be tangent to the curve. This is why I like this example so much. We have the gradient and the cross product. So we start mixing all these things together. All these things that we've talked about that seem like separate topics. We start mixing them together. Chapter 15, everything that we've talked about gets all stirred together in a nice, tasty sauce. But yeah, it's like the culminating chapter of basic calculus.
Basic calculus?
Yeah.
What is beyond basic?
Multivariate.
It's like playing with letter blocks.
All right, so let's do this. Let's say f1 is x squared plus y squared minus z, and f2 is 4 minus y minus z. So we have f of x, y, z equals a constant. So del f1, 2x, 2y, negative 1. And del f2 is 0, negative 1, negative 1. Cross those two. And I'm going to substitute my point in here. So I'm just doing a cross product with a vector, not a variable vector.
Does it matter which order you cross them?
No, because one will give us a vector pointing this way, the other will give us a vector pointing the other way. So it still give us an equation of the line. So del f1 at 2, negative 1, 5, cross del f2, terrible vector symbol, f2 at 2, negative 1, 5 is going to be this determinant ijk, for negative 2, negative 1, 0, negative 1, negative 1. And when I did this cross product, I end up with 1, 4, negative 4. Yeah, I always have to write out the cross product because I make arithmetic errors. All right, so those are our direction numbers. So this is a vector in the direction of the line. So our symmetric equations, this is our point 2, negative 1, 5. So our equation of the line, our equations of the line, x minus 2 over 1 equals y plus 1 over 4 equals z minus 5 over negative 4. All right, let's take a look at that. I should have opened this sooner because it takes Mathematica a while to open. 13, what section are we in? 7. Surfaces. That was 13.3 above.
Sorry.
We already did those.